Okay, welcome to the last section of Chapter 11, Cylindrical and Spherical Coordinates. In this section, we'll learn about two other ways of describing where a point is in space. When we use XYZ, we are using rectangular coordinates, but there are two other ways that allow us to explain where a point is situated in space. So think about polar coordinates in the plane. That was another way of pointing to a place in the plane, and cylindrical and spherical coordinates can be considered to be extensions of the polar coordinates from 2D. So we'll learn all of those, and what's going to be tricky is to be able to switch between them and to sketch surfaces in these new coordinates that we are not so used to. The cylindrical coordinate system is built like that. When you have a point P, you can define it using three other variables. One is going to be how far it is from the z-axis, and this is why it's called cylindrical coordinates, because you could say P is on a cylinder that has radius r. The second coordinate is theta, so on that cylinder, what is the angle I have to travel until I reach the point? And finally, how high do I have to go? With these three values, I can describe each point in space. So in cylindrical and spherical coordinates, the origin is called the pole. Here are the conversion formulas, and to see how we get to these formulas, I'm going to switch to the iPad. So we're first going to look at how we can switch between cylindrical coordinates and rectangular coordinates. So we are going to do in both ways. But we'll start with imagining that we are given a point with its cylindrical coordinates, r, theta, and z. So we know r, we know theta, and we know z. Now we want to try to find formulas for x, y, and z. And these formulas, x is a function of r, theta, z, y is a function of r, theta, and z is a function of r, theta, and z. So that we would be able to just plug in the values of r, theta, and z, and it would give us x immediately, it would give us y, it would give us z. If you look at the figure, you'll recognize an important right triangle here at the bottom, with a right triangle here, and of course we can see that x is equal to r cosine theta, y is equal to r sine theta, and finally z is just equal to z. It's not the same, it wouldn't be the same letter if they were different things. In cylindrical coordinates, z is just the height of the point. So, what about if we were given x, y, z and we were interested in finding r, theta, and z? Well, for the reason I just explained, z equals z. There's no doubt about that. What about theta, and what about r? Let's start with r. It's the same triangle as before, but we're going to use the Pythagorean theorem for that. We know that r would usually be the square root of x squared plus y squared. However, here we're not going to write the square root. We're going to write r squared equals x squared plus y squared. Why is that? Because maybe you remember from polar coordinates that r can be a negative value. If we were given the angle theta, that is here, and let's pretend it's 30 degrees, and r was equal to -2, then the point it would describe would be somewhere behind here. So r has two possible values, and therefore rather than writing r equals plus or minus the square root, we just write r squared equals x squared plus y squared. If r has two possible values, theta has actually a lot more, infinitely more. I suggested theta was equal to 30 degrees in this example. We could also pick, for the point that's behind, a theta that is 150 degrees, or maybe more, 390 degrees, and so on. So there's infinitely many possibilities for theta, and therefore, instead of writing theta equal, we will say tangent theta equals opposite over adjacent. Okay, so let's have a look at examples. When you have to convert points, it's going to be pretty easy. You just have to plug in the values. So if we know that r theta z is 4, 5 pi over 6, and 3, and we want to convert that to rectangular coordinates, all we do is we just use x equals r cosine theta, which is negative 2 root 3, y equals r sine theta, and it's going to give us 2, and finally z equals z, so it's still 3. We can go backwards. If we are given x, y, z, we use the other formulas right there to find the points. So here there's a choice that has to be made. When we find that r squared equals 4, r equals 2, it could also be r equals negative 2. But why make it complicated? R equals 2 is more natural. And then tangent theta equals root 3 over 1, which means theta equals pi over 3 times a plus n pi. But again, why make it more complicated than we need? So the angle pi over 3 is the most natural. Sketching surfaces is a bit more tricky, and we want to just think about what these equations mean. So how can we sketch r equals 3 if it's described in cylindrical coordinates? R equals 3 means all the points such that r equals 3. And there's no constraint on z or theta. So the only thing is, where are all the points such that r equals 3? And the answer is a cylinder. Here's it's shown in red. What about the second one? Z equals r. That's even more tricky. Now, every time z increases, r has to increase as well. For example, if z equals 5, r has to be equal to 5. And if z equals 6, r has to be equal to 6. The result of that is it's going to draw a cone in space. So the higher we go, the wider, or the greater the radius of the circle. And theta is not limited to any angle, so that's why we have a complete circle for any value z. Note also that it works for negative values. If z equals -1, r equals -1, we saw that that is acceptable. So this is why the cone has two sheets, one above and one below the xy plane. Even though I'm not sure we can call it the xy plane if we are in cylindrical coordinates. Lastly, theta equals pi over 3. So what are all the points such that the angle is pi over 3? It's a plane, and theta would be shown from the x-axis to the green plane. So all the points here in this plane have the particularity that their theta is equal to pi over 3. What we did with points earlier, we can also attempt to do with surfaces. So if we are given a surface in rectangular coordinates, like y equals x squared, which is a paraboloid cylinder, how would that look like if we wanted to express that same surface in cylindrical coordinate? This is the easy way, because we can use the formulas we had, y equals r sine theta and x equals r cosine theta, to work our way to reach a nice equation in cylindrical coordinates. It's a little trickier backwards. If we are given an equation in cylindrical coordinates, to find the rectangular coordinates, you have to play around a little bit until you get somewhere. So here there's a double angle formula, first of all, so that means we can write this as r squared times, open parenthesis, cosine squared theta minus sine squared theta, close parenthesis, plus z squared plus 1. And then we notice, wait a second, r cosine theta is equal to x. So this is x squared, this is y squared, and we have plus z squared plus 1. So the third coordinate system is called the spherical coordinate system, and this time, as the name says, it's related to spheres. we can describe any point in 3D as being part of a sphere centered at the origin with radius rho. We choose rho here because r is already used for cylindrical coordinates and it's a different value. So once we have a sphere in space that has radius rho, we can use the same theta as before to move along the sphere, and at that point there would be just a circle of points that have that exact rho and that exact theta, and the last coordinate, which will bring the possibilities down to 1 point, is the angle phi. The angle phi is a little special. It's measured from the z-axis downwards, and it's never going to be less than 0, and it's never going to be more than pi. If phi equals pi, then it would mean we would be on the z-axis going downward. So we'll now look at how we can learn to switch between spherical and rectangular, as well as between spherical and cylindrical. The second case scenario is to switch between spherical coordinates and rectangular coordinates. So this time we will start with spherical coordinates. Let's say we have a point given by rho, theta, and phi. So rho is this length here, theta is the same as before, and phi is that angle up here. And again, we want to find x, y, and z as functions of rho, theta, and phi. So we'll start with z because it's the easiest, but it's also a nice stepping stone to finding x and y. So z is this right here, and we have a right triangle there. Therefore, we can just write that z is rho times cosine phi. X and y are a little bit further away. Let's add the x here. So we were talking about this right triangle before. It would be nice if we had r, wouldn't it? If we had r, we would say that x is r cosine theta and y is r sine theta. Well, r, we can find it because r is also at the top here. R is rho sine phi. So we can, for both of these, we can say rho sine phi, which is r times cosine theta. What about y? Well, again, y is r sine theta, and r is r sine phi. So r sine theta. For the other direction, if we know x, y, z, and we are interested in figuring out the values of rho, theta, and phi, rho is going to be found by using the Pythagorean theorem twice. Rho is x squared plus y squared plus z squared. And this time, because rho is a non-negative number, we can write it as rho equals the square root. We don't have the same issue as r, which could be positive or negative. Theta is the same as before. It's the same as in cylindrical coordinates, so we saw how to find that. Tangent theta equals y over x. Finally, phi is a little bit more tricky, and there's actually a variety of ways to find it. We can use any of the SOHCAHTOA. Let's say cosine phi. Cosine phi, cosine is adjacent over hypotenuse, so the adjacent sine of phi is z, and the hypotenuse is rho. Rho happens to be root x squared plus y squared plus z squared. There's other options. You could try tangent phi, and you can also try sine phi. Sine phi is probably the most complicated because it involves r and rho, which both need to be translated, but it's also possible. Finally, we need to see how we are able to switch between spherical and cylindrical. So let's say that we know rho, theta, and phi, and we are trying to find r, theta, and z. So let's see. R. Well, given that I have phi, and r can also be written up here, it looks like r equals rho sine phi. Now there is a little hiccup, however, and that is that r might be a negative value, and that forces us to define this equality as r squared equals rho squared times sine squared phi, which would include negative values of r, because rho and sine phi are always going to be positive, but r could be negative. Then theta. Theta is just theta. It's the same in both coordinate systems. And finally, z, if I want to express z in terms of rho, theta, and phi, z is equal to rho cosine phi. Good. So lastly, we need to go from cylindrical to spherical, and that means we need to express rho, theta, and phi in terms of the others. Rho is going to be found using this right triangle. It's a little easier than before. This is z, this is r. So rho squared equals r squared plus z squared. Actually, I don't need the square. Rho equals square root of r squared plus z squared. It's a positive value. Theta equals theta, and we are now down to the last one, phi. Phi in terms of r, z, and theta. So again, we're going to use the tangent. We could use cosine, but the tangent is clearly the easiest here. Tangent phi is opposite over adjacent, so it's r over z. Okay, so from here, actually, phi, we could write it as arctan of r over z. Let's update this. Phi equals arctan of r over z. Thank you. Here are all the formulas that you can copy in your notes. Notice that even though r could be any positive or negative number for cylindrical coordinates, rho is always positive or 0 in spherical coordinates. So let's think a little bit about surfaces. If we are given phi equals pi over 6, what does that mean? It means that the angle between the z-axis and the points I'm looking for is pi over 6, and there's lots and lots of options because theta is not limited and rho is not limited, and therefore it's a cone. It's a half cone because it doesn't go below. That would be phi equals 5 pi over 6 if the cone had the second part. Sketch the surface defined by rho equals 2. That's easy. It's just a sphere that has a radius of 2. So if we want to see one last example of switching between coordinates, if we are given x squared plus y squared equals z squared in rectangular coordinates, we can work to try to find the spherical coordinates. And what you do is you just plug in x equals rho sine phi cosine theta, y equals rho sine phi sine theta, and z equals rho cosine theta. And so you put squares everywhere. It's just, well, that was not a good idea, but there's a square here, and then you can factorize and cancel out things. There's another way to solve this problem that leads to cosine squared phi equals 1/2, I believe, which is also correct. So different ways of solving the problem. If you want to graph functions in Grapher, then there's a set of variables that is fixed in the software, and you don't need to tell the software that you are using cylindrical coordinates, but you need to type R0, theta, and Z. How do you type R0? It's R, and then, okay, let me fix this if I can. How you represent, it's R with a bar and 0. Theta, you just spell it out, Theta, and rho and phi, you can just spell them out as well. So there's no rho, sorry. Instead of rho, it's R, and instead of R, it's R0. Phi, you just spell it out, Phi.